always hesitant to draw diagrams. So what have we seen last time? And we'll talk about the origins of these things a little bit more, but if you have magnetization per unit volume, you can have these bound currents given by, and what we did this is, and a surface current is M cross N unit vector. This is the surface current, this is the outward normal. Unit normal to compute the surface current. And we got this only by just vector analysis. Yep. We didn't intuit a reason. But vector analysis is a good way, is the correct way of getting it. That's the math. But we'll also talk a little bit more about the physics of it. But before we get started, I want to do one problem, and it refers to a previous problem. So let me describe this problem and what it's referring to. So what I want to do is example 6.1. So what you have is a sphere with uniform magnetization. So M is given to you. It's a uniformly magnetized sphere. Yeah? It wants you to find the B field everywhere. The whole point is this might induce a certain current. So let's compute the bound. So these bound currents, I think I may have mentioned this. So these are these loops, right? The currents are moving. Why do we call them bound if they're moving? Well, these currents are moving in a circular, or somewhat localized pattern. When bound current distinguishes itself from free currents, like so. In a free current, you will have electrons moving from one part to the other. Here, it is usually just moving around the nucleus of the atom, or even larger, complicated structures. Be it molecules and whatnot. Okay, that's what makes it bound. The charges are moving, but it's restricted to a localized area. Now, this is somewhat convenient because J is 0. There's no other current. You just have a magnetic material. You have a magnetic material. We don't know how this was created, but it has a uniform magnetization M. So the curl of M is 0 because it's a constant vector. So it is implied in this problem that it's constant. It says uniform magnetization. But on the other hand, KB is M Z hat cross R hat. Z cross R, what's the direction? Correct. The angle between Z and R is theta. So it's M sine theta phi hat. So this is the only current. So we'll do this problem by recalling another problem. There's no volume current, there's a surface current. So here, I just want to make sure that this is clear to you, that there's no divergence, it's uniform. On the other hand, you have this is R hat, the outward normal. As a result, we have currents in the boundary currents in the along the surface. Okay. We did a similar problem, which was an example, and I want to, no point redoing the facts. It was a long calculation. So recall example 5.11. Here, what you had was a uniformly charged sphere, shell rather, that is spinning. So you had and on this was a sigma. In this problem, we had that K, but K is always equal to sigma V, but V, as you know, if it is spinning around, V is omega cross R. That's when we confronted the R cross omega versus omega cross R. And when you do omega cross R, well, you get omega R sine theta. So by analogy, this problem is exactly like this problem, where you identify sigma omega R, you simply replace it with M. So thankfully, we don't have to redo this problem. Yeah? So this, you compare it to this. The source is very different. This comes from magnetization. This comes from somebody spinning it. But the effect is the same. So we have done this problem, and I'm just recalling the results. There's one important feature here that we may actually get to use. I don't recall seeing it. It should be there. Huh. I'll look for it. There's got to be a larger discussion. Anyway, yeah, but so we had, in this case, found out that the B inside, in this problem, I'm just copying it from our notes, it was 2/3 mu naught sigma R omega, and B out was same as that of a pure dipole. You can look up the expression. Okay, so all we have to do is make the analogy of sigma R omega. So for our case, and I'm going to write both of them down, by the way, B in sigma R omega is replaced with M, and you will find 2/3 mu 0 M. It's a uniform B inside. And B out, I'm just copying down from the previous example, really, the expression for a magnetic field due to a pure dipole. I think what we did was we found the vector potential, and then we took the curl of it. And I'm just writing this result, and you might say, well, why am I writing it? Just to make one point. In this case, this is the magnetic moment little m of a pure dipole. Well, we don't have a pure dipole, but we have a uniform M. The magnetization per unit volume. So I need to write this in terms of m. That's easy. I'm not going to rewrite the equation. Little m is going to be m times what? 4/3 pi r cubed. Just sort of re-emphasizing the relationship between m, lowercase m, and uppercase m. Uppercase m is magnetization per unit volume. In this case, it's uniform, so if you multiply that by the volume, you get it. So if I take this and place it here, that would be the answer to this problem. Yeah? Any questions? Chip?
I'm taking all.
Yeah.
Okay. So, when for example,
Where are you? Here?
yes.
Okay.
When
So,
we
yeah.
are doing like Z cross R there,
Z cross R. Yeah.
so Z hat and phi hat, how, but those are two different coordinate systems.
They are different coordinate systems, but you can still use the right hand. So you are right. So these are good questions. So suppose you have a sphere and you have an outward normal, and then you have Z. You do this, it's still going to be tangent to the sphere. Now, when in doubt, you can do this, right? You do this. Well, this is going to be R on the sphere. And then you do Z cross R. Then convert it to phi coordinate system if you want. Yeah. So we can do it the brute force way, or you can use the right hand rule. Yeah? We still know that they're perpendicular. See, R is perpendicular to the sphere.
Yes.
So if you take a cross product with R hat in it, it has to be tangent to the sphere. So it has to be some component of phi or theta.
Okay, yeah, that makes sense.
Yeah, surely it's not theta.
Yeah, that makes sense.
Yeah. Yeah. But otherwise,
Yeah.
this is the way to go. But the rest worked out okay? I mean, I know we're just copying it down from a previous problem. I think this is an important result to get the magnetic field. It's just like we did that for a dielectric material. We found the the electric field inside a uniform sphere of a dielectric material. It was constant. And we used that to compute, to argue that the expression we have is the correct expression for the average dielectric field. I don't particularly recall, but I think the same argument goes into for the magnetic field. We may need that, but nonetheless, B inside is uniform. Okay, so we have the correct answer, this. Let's see, and I think Martin alluded to that last time. Can we get a heuristic description? And this is, again, beautifully done in Griffiths. I'm just repeating the argument. My pictures are not as pretty as Griffiths' textbook can be, but you have the textbook already. So I'll do this in 2 steps. again, the argument here is exactly Griffiths' argument. So first, I want to show this result. So let's consider a slab of magnetic material. And to show that it's a slab, I'll do that. Okay? And consider for the moment M uniform. In fact, let's make this Z hat. So what you have are these tight loops of magnetic dipoles. I should have made them uniform. You know, these small loops of magnetic dipoles. So what I'm going to do is pick two dipoles that are adjacent to each other, but I won't draw them adjacently so that you can see the diagram. I'm going to just sort of separate them so I can draw individual loops of currents. So, and I'm afraid for the video it might be too small. So let me even do this. You have a material here, and you have and I'm going to just separate them so that you get to see what's going on. In both these cases, it's a uniform magnetic field, so I will have M this way. Yeah? And now let's draw a current loop. Again, the current flows this way because M is that way, just the right hand. And as you can see, the only place a net current will result is in the boundary. Because look, this is going inward, this is coming outward. They cancel each other. So you could get a K along the surface. Yeah? Now let's do a little bit of dimensional analysis. I'm going to call this, it was confusing when I saw Griffiths use the symbol T for thickness, I'm assuming. And you know what I stands for, and I is the current. A is the area of the loop. So this sort of a cross section is A. So on the one hand, I would have little m equal to I times A in magnitude. But I also have little m to be magnetization times this is magnetization per unit volume. So A times T. Yeah? So I compare these two. IA equals MAT, or I is MT. But look at this. This is the thickness. So what is the magnitude of K? It's the current divided by thickness. K, right? The current flowing divided by the perpendicular thickness. That's what K is. It is I over T, which is exactly M. So K has a magnitude of M on the boundary. KB, I should say, has a magnitude. I should use KB. And that's great, because this seems to suggest that as well. So in this surface, M is pointing upward, N is pointing outward. M is this way, K is that way. Can you confirm that this cross this will point in that direction? That's easy. Guess from the diagram. Yeah? So indeed, this is the vector calculus explanation. This is the heuristic explanation. So once again, M points upward, K points outward. In this coordinate system, N points outward, K is in the x-axis, so to speak. So I would get M cross N is in the x-axis along K. So that works out perfect. Yeah? Why did Griffiths choose a uniform magnetization? Well, for one thing, he didn't want to talk about J at the same time. We wanted things to cancel out uniformly. That's the argument. Now, this one. Here too, he's very clever. Although it's really testing my diagram drawing skills. So, this is my y-axis, z-axis, and this is x-axis. Obviously, I'm going to look at a chunk of material. And in the chunk of the material, I'm going to pick two small M loops. And what I don't want is for the magnitude of M to be the same. Because if the magnitude is constant, I won't get a curve. So I need to find a clever way of drawing two adjacent rectangles with one M larger than the other M. So let's compare the magnitude to the size of the volume. And so he draws two rectangles. So here's one rectangle. And I have some M. This M is distinguished by its location at some Y. So this is well, I'm not saying, so I'm going to change that diagram before you draw it entirely. At the moment, I'm just looking at the z component, just to keep track of what's going on. Now, adjacent to this, there is another rectangle. First of all, I won't make them exactly adjacent because it's hard to draw the diagram. So I'm going to make it a little further away. And I'm going to make the rectangle bigger. Why am I drawing the rectangle bigger? Suggesting that slightly away, m is larger than this guy. Now this is m of z at some location y plus delta y. Yeah? Now, on this side, there is a current loop like so. On this guy, yeah? Because the value of m here is larger than the value of m here, the magnitude of the current here is less than the current here. Correct? So this, just from this contribution, and I have to be careful how I partition my diagram, I will get what is okay, I will get a net current in the x direction, correct? Small going in, coming out. And how much will that be? Well, that's equal to mz at y plus delta y minus mz at y times the thickness dz. Why is that the case? Because from last time, we know that the magnitude of k and magnitude of is equal to the magnitude of m. So this is the k times.
Well, we have the I is equal to mt, right? You just
I is equal to, yeah. I
is
is
equal to mat.
Yeah, yeah. Yeah, same argument. Now this can be approximated as, this is almost the, take the z component and take the derivative in the y direction, and then I can put it as dy dz. Yeah? I'm going to put plus, I'll draw another diagram. we'll see where else could an I component come from. Okay? But this is coming from the Z component of the magnetic field. As a result, Kx is the current flowing through this area divided by, J. Divided by the area. That's what volume current is. So it is simply this term. Now, if you have forgotten, let me remind you of how this was defined. J was defined two chapters ago. See, J di over the area perpendicular. That was the definition of J. So we have the current here, and if it's the current is in the x direction, what is the perpendicular area? dy dz. So I have obviously, so let me leave that here. J equals di over dA perp. So over here I've left a blank, I have left a blank. I need to fill that in. Where else could the I component, we're only calculating the x component of J. And we can say similar remarks apply to the y component and z component. So there is another diagram that we need. And so that I don't mess the same level of detail, I'll need the same portion of the blackboard. So let me do it this way. This is my y. I want to change the orientation. Z. Here we looked at the z component of m alone. Now let's look at the y component of m. So to do that, I will look at two rectangles here. And to suggest that this one is stronger, I'll make this a larger rectangle. And I would have my at some z, and over here I would have my at z plus some dz. In this case, I used blue, so I'm going to continue to use blue. I'll have some current here, some current here, some current here, some back current here. And this is a smaller rectangle. What do you notice? This area, this length over here, I'll let you copy this down. So I made the same analogy, As Z increases, the magnetization is increasing to be consistent in notation. What do you notice? Here, this volume being bigger, and maybe I'm not drawn it properly, all dimensions being bigger, this I is more than this I. And this is pointing in the x direction. Therefore, exactly similar term will appear, except z is replaced with y, and y is replaced with z. Look at this. Z, y, y, z. Only difference is, which way is the larger current? Inward. So the plus is not a plus, but rather look, this is a bigger area than this area, right? This area is a bigger area than this area. This current is pointing outward. This one right here. So this is pointing outward.
The base of that one.
Base of this one is pointing inward. And that being a bigger cuboid, the bigger trumps the lower. So it's a minus sign. That is very good because you will see that this is nothing more than, first of all, this is the bound current, del cross M, the x component of the cross product.
Why don't the other sides of the current, like, they don't have any effect on it?
No, I'm at the moment only worried about the x component. You know, what's good for the goose is good for the gander kind of thing. The y and z component works out the same way. I'm showing, heuristically showing that this is true in the x component. You're free to draw two more sets of diagrams for the y and z component, but why would you? It's exactly the same way.
So when we're doing this, we're only looking for x component.
We're only looking for the x component. Now you might say, well, wait a minute, if I move it this way, will I get an I contribution? I leave it for you to see that you won't get an I contribution. You'll only get a contribution when you draw that similar diagram in the y and z component. So when I say dot dot, it's really one dot. There's only one other missing term. So indeed, our intuition matches the exact mathematical answer. In some ways, this is physics, huh? This is how we learn how things are put together, especially in the sciences. I don't care if it's chemistry, biology, physics, in the observational sciences, this is the intuitive, perhaps non-rigorous argument that precedes any great insight. In this particular case, I don't know what preceded what, because the vector analysis seems fairly simple enough, but it certainly doesn't lead to any intuition. So the skilled scientist should learn to intuit, and that's where science becomes an art and not just a craft. It is the artist that triumphs.
So let's rotate our boxes, put them on the x.
Yeah.
The reason why there's no component is because our loop has no x piece at all.
Right. I mean, you can talk about a mx,
Yeah.
so the current is in the yz plane.
Yeah.
Yeah.
Okay.
Okay. Simple idea, but we still have to go through. So what we have also seen is the fact, I'm going to go through this, I hope, rather quickly. I want to finish at least this today, is the fact that when you have a magnetic dipole, there's a torque, and the torque is M cross B. Yeah? So we know that if you turn on a magnetic field, if the dipole is indeed able to rotate, it can either align or misalign. And with the dielectric, we said it would always align because the misalignment is unstable. Here, the problem is, in a material, you have to make the molecules turn around, spin the other way. That is not so easy. And there's another effect that creates, that's what I'm going to talk about. So in reality, two things can happen. You can have it where M aligns with B, and those kind of materials are called paramagnetic. And the other one is diamagnetic. And I'll show you a little bit of a heuristic argument for this one. The argument is completely wrong fundamentally, but we have always learned lessons from not the most fundamental thinking. Again, this is where art triumphs craft. Okay? And there's a third class, and that is ferro. I don't know how many R's. Sounds like it should be 2 R's, right? Like iron, ferrous. Yeah, ferro. So, this is easy enough that it doesn't really require justification. Yeah? This is counterintuitive. This is just impossible to explain classically. All of these things are only truly explained using quantum mechanics. But let's look at a simple case. And the haste in mind, I'm just going to bang away, huh? So this argument is flawed. It is not fundamental. It is to see what causes for a dipole to be, when a magnetic field is turned on, to be anti-aligned, or a little more anti-aligned than before. What would create this bizarre effect? Actually, it is caused largely by the spin of the electron, and not because of the orbital velocity. But the orbital velocity also creates a little bit of a anti-alignment, and this is the hokey argument I wish to present. So imagine, if you will, just a hydrogen atom, and you have an electron moving this way, and here's the electron. And I'm going to look at this electron, and I know the velocity of the electron is 2 pi r over t, the period. And I also know current equals charge per unit time, and one electron does not constitute a steady current, but as Griffith says, if you don't blink too fast, you'll think of it as a current, and so it's one electron. That's going to be my current, charge over time, and so this is minus E. I'm going to substitute this over here, and I get 2 pi r. That's the current. And the magnetic moment of this atom is I times A, so minus E V over 2 pi r, the current, times pi r squared z hat minus E. There's not much going on other than algebra here, so I'm going to write it like so. And when an electron moves in a circular path, the centripetal acceleration is given by Coulomb's law. On the one hand, you have mv squared over r. On the other hand, you have kq squared over r. So k, 1 over 4 pi epsilon naught, q squared. We know it's attractive, so I'm just writing the magnitude over r squared is mv squared over r. Okay, so now let's assume you turn on the magnetic field. And we'll be nice enough to turn on the magnetic field in this direction. As you turn on the magnetic field in the z direction, you're going to get an additional force on the electron. You're going to get a V cross B. Yeah. What direction is V cross B going to be? So this is a circle, and V is this way, B is this way. V cross B is inward if it is a positive charge, but outward if it is a negative charge. So for mv squared, and you get a new velocity, I'm going to call it, so turn on V, call the new speed, V bar. And so you will get Coulomb's law. Plus EVB, EV bar B, because this is now an additional force. That's equal to mv bar squared over r. They both, the net centripetal force is mv squared over r. You add up all the radial forces, that has to equal to mv squared over r. If it's moving in a circular path, gosh, we know that electrons don't move in a circular path. Have you seen all the nuclear physics posters that look like this? Yeah, it's not happening. Okay, I'm going to solve for this term. Again, nothing much going on, but algebra and wrong physics. Don't get me wrong, I like wrong physics, not in exams, of course, but otherwise. Yeah? Now, the magnitude of V and V bar is not going to be that different. I mean, it's not going to change drastically. Don't turn on, like a neutron star magnetic field or anything like that. So I'm going to call this delta V. So V bar in magnitude is approximately equal to V. So this sounds silly, but the whole thing is rather silly. And I'm going to replace this with 2V. They're roughly the same. And then I get that delta V. I'm going to solve for delta V. Delta V equals, well, you can see this. This also becomes a V. So V and V cancels. There's a 2. And so I get E R B over 2M. Yeah? So let me make it clear. EVB equals M over R delta V times 2V. So the V's will cancel. So delta V equals EBR over 2M. Here M is the mass of the electron, mind you. So the point here is, because of the change in velocity, there's a change in the magnetic dipole moment. Look, I'll get a delta M, which is nothing more than minus E delta V R over 2 Z, which is minus E R over 2 E V R over 2 M, and that's minus E squared B R squared over 4 M Z hat. I hope that is what Griffiths has. Yep. Or I can combine these two. And to wrap it up, I notice that the electron has gained a little dipole moment against the magnetic field. Chip, don't fight this one too hard. This is just an algebraic shuffle that we have done. It is not really kosher physics. This is not what's happening in an atom. The spin is also very important. Yeah? But the lesson we can take away, we want to take away because it's observed, we have to somehow explain this, is that when you turn on a magnetic field, you gain a little bit of dipole moment in the direction opposite to the magnetic field. So there are classes of materials where there are many electrons with random direction, all of a sudden it gains a little, and the net dipole moment may be, in arbitrary direction, maybe even cancels out. But the moment you turn on a magnetic field, because of such contribution, everything gains a little dipole moment in the opposite direction. So it is conceivable by this wrong argument that these things could exist. That is reality. This is a fact.